This is a Van de Graaff generator. Let me turn it on. A Van de Graaff generator is a simple way to get to high DC biases. I purchased this one, but I have built several of them. They are very simple and inexpensive to build. The operation of the Van de Graaff generator is based on the triboelectric effect. If you put two materials together, you will have a transfer of electrons from one to the other. For instance, if you put glass and rubber together, initially you're going to have transfer of electrons from the glass to the rubber. But this will not continue because the rubber is becoming negatively charged and the glass positively charged. So you have an electric field that builds up to transfer electrons in the opposite direction, from the rubber to the glass. In equilibrium, these two transfer mechanisms will balance. I will explain how the triboelectric effect is used in the Van de Graaff generator to get to high DC biases. The dielectric breakdown strength of air is about 30,000 volts per centimeter. I have to get about 10 centimeters away to get a spark to occur. So the potential difference between the generator and my arm is about 300,000 volts. I can feel these sparks, but they're fairly mild. That's because very little charge builds up on the Van de Graaff generator to get us to 300,000 volts. Let's determine how much charge builds up on our Van de Graaff generator. My Van de Graaff generator is about 16 centimeters across, and it's about 12 centimeters high. This is a shape that would be difficult to analyze, so we will approximate our Van de Graaff generator with a sphere of radius 7 centimeters. What we want to determine is how much charge is on the sphere when it reaches 300,000 volts. With a charge Q on the sphere, this is the form of the electric field intensity outside our Van de Graaff generator. Assuming there is nothing near the sphere, the potential of the sphere is the potential difference between the sphere and infinity, and that can be found by taking minus the integral of the electric field intensity from infinity to the sphere, and that works out to be the charge on the sphere over 4 pi times the permittivity of free space times the radius of our sphere, 0.07 meters. We can then solve for the charge on the sphere, and we find that it is 2.3 microcoulombs. Another way of thinking about this is that the charge on the Van de Graaff generator is small because the capacitance is small, capacitance being the ratio of the charge to the potential. So for our Van de Graaff generator, the capacitance is approximately 7.7 picofarads. Assuming the spark lasts for 1/10 of a second, the current that's going to flow during that 1/10 of a second is our charge, the 2.3 times 10 to the minus 6 coulombs over our 1/10 of a second. This small of a current flowing for 1/10 of a second is why I could place my arm close to the Van de Graaff generator and have sparks flowing between the generator and my arm. The product of voltage times current is power. 300,000 volts times 23 microamps is a power of 6.9 joules per second. During the spark, the voltage will go from 300,000 volts to 0, so we really don't maintain this power for the full tenth of a second. But assuming the power is maintained at 6.9 joules per second for a tenth of a second, that would mean the spark would deliver an energy of 0.69 joules. This amount of energy is equivalent to the energy it would take to lift a 1 kilogram mass 6.9 centimeters on the surface of the Earth. And we know that these sparks are delivering less than that amount of energy, so there's not a lot of energy being delivered by those sparks. Let's now explain how the Van de Graaff generator generates such high DC voltages. The Van de Graaff generator consists of our metal top, and inside there's an electrical connection to it to a wire. Here we have a rubber belt that's being turned on an axle, so there's actually contact between the axle and the rubber belt, and a glass tube that's also making contact with the rubber belt, but I'm showing gaps for illustrative purposes. The wire that's attached to the inside of our metal sphere comes close but does not touch the rubber belt. There is another wire attached to ground that also comes close but does not touch the rubber belt. As the motor axle rotates, it will cause the rubber belt to rotate, and the rubber belt rotating will cause the glass tube to rotate. From the triboelectric effect, glass and rubber in contact will result in electrons transferring from the glass to the rubber. As electrons transfer from the glass tube to the rubber, an electric field sets up that would drive electrons from the rubber to the glass tube. And eventually, equilibrium would be reached when those two processes are equal. But the rubber band and the glass tube are rotating. The electrons get spread out over the area of the inside of the rubber band, which is a much greater area than the area of our glass tube. In the vicinity of the glass tube, there will be a very large electric field because of the large amount of positive charge compared to the negative charge, and that will pull electrons to the tip of this wire that's connected to the metal sphere. When the field is high enough, electrons will be pulled off the tips of these wires and deposited on the rubber band. This leaves our metal sphere positively charged as electrons are continually pulled off of the metal sphere. Once the rubber band gets sufficiently charged negatively, those electrons will start to be removed due to this ground wire. The negative charges on the rubber band will repel electrons from our wire that's attached to ground, making the tips here very positively charged. The electric field emanating from these tips will spread out, so it will be very large in the region of the tips. This large electric field in this region will pull electrons off air molecules, making them positively charged, and the electric field will eventually cause them to work their way to the rubber belt, and thereby neutralizing a negative charge on the rubber belt. The Van de Graaff generator will continuously pull electrons off the metal sphere to ground, resulting in high DC potentials on the Van de Graaff generator. This is a Leyden jar capacitor that I constructed. It has about 1,000 times the capacitance of our Van de Graaff generator. If I make an electrical connection between the Leyden jar and the Van de Graaff generator, I essentially have the two capacitors in parallel, so the overall capacitance will be about 1,000 times greater than that of just the Van de Graaff generator. Now for a given potential, I'll have about 1,000 times the charge. That amount of charge would be very painful or even lethal. So instead of using my arm to discharge the Van de Graaff generator, I will use this discharge rod that I constructed.